objective of the upcoming experiment is to verify Hess's law. To check, is Hess's law actually true? You can see for yourself. Is the delta H, is the heat of this reaction the same experimentally as by calculating it using Hess's law from the heats of two other reactions? Can we find that H3, the heat of that third of this reaction, is able to be found by combining 1 and 2 as well as experimentally? So, to do this, first I want to say that yes, we will be doing these experiments in the coffee cup calorimeter. We're going to find the delta H's of those reactions 1, 2, and 3 using the coffee cup calorimeter, which is just like in your calorimetry video earlier. So you're going to see how much heat is released by this reaction. You'll find that by seeing how much heat was absorbed by the water and the calorimeter. Now, the heat of that reaction is the negative of the heat of the water and calorimeter, but you don't know what the heat of the calorimeter is without knowing the heat capacity of the calorimeter. So really the new part of this lab is to find the heat capacity of your calorimeter. So as the calorimeter changes a certain number of degrees, how much heat is absorbed by it? So rearrange this equation. The heat capacity is the heat absorbed by the calorimeter over the change in temperature that it undergoes as that heat is absorbed. So to calculate both of these, what we're going to do is we're going to have a cold coffee cup calorimeter, and we're going to add 50 grams of cold water to it, and then we're going to add 50 grams of hot water to it. We'll know the temperature of both of these things. Now, when we combine these things, there is a theoretical average temperature which they should acclimate to. However, it's likely that we will not find that the water in the cup is the average temperature, but a little bit colder than that, because that water will release some heat to the cup, to the styrofoam. And so we want to see how much heat is released by the water and therefore absorbed by the cup. So the heat absorbed by the cup is the negative of the heat released by the water. Now you're going to have 50 grams of each of those two waters solutions, so you're going to have 100 grams of water, and you know the specific heat of water is 4.184. You're trying to find how much water, how much heat was lost from the water. That's the difference between what the temperature should have been when mixing and the actual temperature that you found when mixing. Now, you're also going to find what is the change in temperature of the calorimeter as this occurs. So the calorimeter was initially cold, probably around 25 degrees Celsius, and soon it's going to be the temperature of mixing as well, the temperature of the water when it has equilibrated with the water. And so the change in temperature of the calorimeter is the temperature of mixing minus temperature initial. And so that should give you the heat capacity. By the way, when you're trying to find the temperature of mixing the two water solutions, you're going to create a graph of temperature in degrees Celsius versus time, and you'll find that the temperature slowly falls, and so your data points are going to be continually falling, though not in a perfectly straight line. And so really what you want to know is, because when you initially mixed them and there was a lot of stirring going on and it took a while for some equilibration, your data is going to look a bit messy soon after the mixing. But you want to consider what was that temperature of mixing theoretically right when you mixed it, or what should it have been. So considering that the same amount of heat is lost to the environment at every moment, more or less, you're going to build a graph, which is a straight line, through those data points. And where that straight line intersects with time 0, that should be the temperature of mixing. All right, thanks for watching, guys.